Hello class 10. I hope you've checked the 3 videos whose link I've sent. Okay, all 3 videos have to do with work done. All right, if you haven't checked, if some of you haven't checked it yet, all right, first go through those videos, then after watch this video. Okay, because in this video I'm going to give you an overview of what work done is, all right, and how it's measured and its different units. Okay, so if you haven't seen the video yet, go through that video, go through those 3 videos first, then have to come back and watch this video. Okay, all right. For the following topics also, the topics to follow, like energy, power, and the topics in different other chapters given in the book. Okay, I'll be sending this way only. I'll be sending you the links to already, some pre-existing good videos that's there in YouTube. All right, then after we might discuss the topics, in our own video like this. All right, so this video is about work done. Okay, so the definition of work done is work is said to be done when a force acting on a body produces some displacement on it. Okay, so for work to be done, there is 2 pre-existing criteria. Remember, there has to be a force acting, and there has to be some displacement produced. Remember that. Okay, because some cases what happens is there is force acting, but there is no displacement produced whatsoever. Like for instance, when someone is trying to push a concrete wall, all right, push a concrete wall meaning there is force acting, all right, but of course the concrete wall is not going to move, all right, so no displacement produced whatsoever. Okay, so in that kind of a scenario, remember the work done is 0. There is no work done, so to say. Now, measurement of work. Okay, how is work measured? All right, work, remember, is the product of the force acting, the displacement produced, and the cos of the angle theta between the force and the displacement. F, remember, is the force acting, S is the displacement produced, theta is the angle between the force and the displacement. Okay, now it's not, see, when force is acting on a body, it's not necessary that, like for example, in this case, I'm trying to push the pen is pushing the pen cover. So in this case, the direction of the force acting and the direction of the pen cover is the same. Okay, but it's not always true. Now if you've checked the second video that whose link I had sent, okay, there was this nice example of a trolley bag being pulled. All right, now a trolley bag is pulled in this direction, so the force acting is in this direction, F. Okay, and the displacement produced, the trolley bag itself moves in this direction. You are pulling the trolley bag this way, all right, but the trolley bag in itself is moving in this direction. So the displacement of the trolley bag is in this direction when the force acting is this. So what is theta? Theta would be, in that case, this angle. Okay, all right. So remember, so work done is the product of force, displacement, and cos theta. Okay. I can actually, I think I'll make a separate video to show you why this cos theta component comes, okay, or how this cos theta component comes, okay, but that would be in a separate video. But for now, you have to, you have to remember this formula. Remember that work done is F S cos theta. In some books, it might be given F D cos theta, where D will be the displacement. Okay, all right. So, keeping the formula in mind, work is Fs cos theta. Let us discuss 3 different cases. Case 1, when theta is 0. Theta is 0 meaning the force and the displacement are in the same direction. Okay, like in this example, when I'm trying to push the pen cover, the displacement of the pen cover is in the same direction as that of the force acting. All right, or another example could be, when I let this pen cover fall down. Okay, another example could be a piece of chalk. When you let it go, it falls down. All right, so that would be why does the piece of chalk fall down? It falls down because of the force of gravity. The force of gravity, mg, is acting on it. All right, and the displacement. So the force of gravity is acting vertically downward, and the piece of chalk also falls down vertically downward. So this is an example of the force and the displacement being in the same direction. That is a case of theta being equal to 0. So if theta is 0 degrees, from this formula, from the above formula for work done, Fs cos theta, when theta is 0 degrees, cos of 0 degrees, if you remember from trigonometry, okay, cos of 0 degrees is 1. So therefore, work will be F into S, since cos 0 degrees is 1. Okay, Next case 2, when theta is 90 degrees, that is when the force and the displacement are perpendicular to each other. Okay, all right. Now that would be a scenario like, in a book there is this example of a coolie carrying some load and moving along the horizontal. Okay, but the force of gravity, of course, is acting vertically downward. So the question is like, what is the work done by the force of gravity, okay, when the coolie is moving, carrying some load and moving along the horizontal? All right, okay, so this would be an example of theta being equal to 90 degrees. So the question is like, what is the work done by the force of gravity, remember? So since in this case theta is 90 degrees, so work done will be 0, since cos of 90 degrees is 0. Okay, and case 3, when theta is 180 degrees, that is when the force and the displacement are opposite to each other. So what would be a good example of this is, I have a stone, or again a piece of chalk, and I'm throwing the piece of chalk upward. All right, so the piece of chalk goes upward. All right, so the displacement of the piece of chalk is in the upward direction. Of course, it's not going to go upward forever. Okay, it is going to fall down, of course. Okay, but we are only looking at the scenario when it's going up. So when it's going up, the force of gravity, of course, is acting vertically downward. So mg, the force of gravity, is acting vertically downward, but the displacement of the piece of chalk while going up is in the upward direction. Okay, so this would be a scenario of the force acting when the piece of chalk is going upward. Of course, the force acting is force of gravity, which is vertically downward. All right, so force of gravity, this is a case of force of gravity and the displacement being 180 degrees to each other, at an angle of 180 degrees with respect to each other. That is, they are opposite to it. The force and the displacement are opposite to each other. Now when force and displacement are opposite to each other, I don't think you know this, but do remember cos of 180 degrees is -1. All right, so since cos of 180 degrees is -1, so therefore from the above formula, W is Fs cos theta, we get W is equal to minus of F into S. Okay, so these three cases, remember, theta is 0 degrees, theta is 90 degrees, and theta is 180 degrees. Oh, one more thing, one more example I would like to give you, theta being equal to 90 degrees. Okay, let me draw it over here. Theta being equal to 90 degrees, when, say for example, I take a stone, all right, and it's tied to a thread, and I go on whirling it, and say for example I'm rotating it, whirling it in this direction. The stone is being whirled in this direction. Okay, all right, so what happens is, you've learned in chapter number 1 that for anything to go round about a circular path, like for example the earth going round about the sun, the electron going round about the nucleus, all right, likewise this stone tied to a thread being whirled like this. Okay, so the stone is going like this, round and round about. So what happens is, this is only true when there is a force which is called centripetal force, which is directed towards the center seeking force. We discussed about it. All right, so this is a case of force acting in this direction at any point. Say for example the stone reaches over here, the force is acting in this direction. So the force is always directed towards the center. That is why it's called the centripetal force or center seeking force. So at any point, say for example this point, the force is directed this way, but the displacement of the stone is directed along the tangent. At this point the displacement is directed here. At this point the displacement is directed this way, such that, say for example, at this point you let go of the string, the stone will travel along this direction. At this point you let go of the string, the stone will travel along this direction. So at this point you let go of the string, the stone will travel along this direction. Okay, so that would be the direction of displacement, remember. Okay, so in this kind of a scenario also we see that the direction of the force and the direction of the displacement are at 90 degrees with respect to each other, are perpendicular to each other, remember. So this is another example of theta being equal to 90 theta being equal to 90 degrees, in which case the work done will be 0, remember that. Okay, now of these three cases I would like to stress on case number 1 and case number 3. Why? Because when theta is 0 degrees, we see work done is F into S. All right, work done is F into S, or work done is positive. Whereas in case number 3, you can see the work done is negative. All right, remember, whenever work is positive, or for that matter, whenever force and displacement are in the same direction, we say work is done by the force. Okay, I repeat, whenever force and displacement are in the same direction, we say work is done by the force, in which case the work done is positive always. All right, and case number 3, whenever force and displacement are in opposite direction, we say work is done against a force, against the force. Okay, in which case the work done is negative. Remember, negative work means work is done against the force, in which case force and displacement are in opposite direction. Work done is positive means work is done by the force, in which case force and displacement are in the same direction. Remember that. Okay, now one last thing I want to discuss over here is the unit of work. The SI unit of work is joule, denoted by a capital J. All right, from this formula, from this expression for work done, Fs cos theta is a trigonometrical ratio. Okay, doesn't have a unit. The unit of force is Newton, SI unit. The unit of SI unit of displacement is meter. So the unit of work done is Newton meter. All right, Newton meter in SI. Okay, so instead of saying Newton meter, it's called joule. 1 Newton meter is also called 1 joule, denoted by capital J. This happens to be the SI unit of work. All right, likewise, when we discuss in terms of CGS unit, cos theta doesn't have a unit. The unit of force is dyne. The unit of displacement is centimeter. So therefore, CGS unit of work is dyne centimeter. Dyne centimeter, which is also called erg. This is the CGS unit. 1 erg is 1 dyne centimeter. Okay. You have to find the relation between joule and erg relation. Okay, so 1 joule is 1 Newton meter, which is equal to 1 Newton is 10 to the power 5 dynes. I hope you know how to convert 1 Newton to dynes. So 10 to the power 5 dynes, 1 meter is into 100 centimeter. So this becomes 10 to the power 7 dyne centimeter. So 1 joule is 10 to the power 7 dyne centimeter, or 1 joule is 10 to the power 7 ergs. Learn this. Okay, so this much for this video. Okay, anything else, any confusion you have, any doubt you have, you can always let me know in the group, or you can write down in the comment. Okay, all right, thank you.